Capacitors. A capacitor is a system of two conductors separated by an insulator. The conductors usually have equal and opposite charges, leading rise to a difference in potential. The conductors are charged by connecting them to opposite poles of a battery. The capacitance of a capacitor are dependent on the geometric configuration of the conductors and the dielectric ability. Capacitance. Two conductors at different potentials have different capacities to hold charge. Capacitance is the capacity of a conductor to hold electric potential. Capacitance depends on the magnitude, shape, and surroundings of a conductor. If the charge on a conductor is increased, its potential increases too. Its charge, Q, is directly proportional to its potential, V. Q is proportional to V, therefore Q is equal to CV, where C is the proportionality constant. This is the capacitance of the conductor. Capacitance of a conductor is the ratio of its charge and potential. Its unit is farad. The capacitance of a capacitor is 1 farad when 1 coulomb of electricity changes the potential between the plates by 1 volt. 1 farad is equal to 1 coulomb by 1 volt. Parallel plate capacitor. A parallel plate capacitor is the simplest form of capacitors. There are two parallel conductor plates, P and Q, in a parallel plate capacitor. Each plate has an area A. If they are located at a distance d from each other and they are connected to opposite poles of a battery, plate P will develop a charge of plus Q, while plate Q will develop a charge of minus Q. The charge would be distributed equally on both plates. If distance d is much smaller than area A, an equal electric field is formed. When the space between capacitors is filled by a different material, it is occupied by air. This air acts as resistance between the plates. If the plates have an area A, a distance d, and the air has a permittivity of epsilon naught, then E is equal to sigma by epsilon naught. E is equal to Q by epsilon naught A. Hence, sigma is equal to Q by A. As there is a uniform electric field between the plates based on the potential difference V, E is equal to V by D. Based on the above two equations, Q by epsilon naught A is equal to V by D. But as C is equal to Q by V, C naught is equal to epsilon naught A by D. When there is resistance between the plates, C is equal to epsilon A by D. By filling the place between the plates by resistance, capacitance increases by K times. Hence, C is equal to K C naught, where C naught is the capacitance in absence of a resistance and K is the resistivity constant. Hence, C is equal to K epsilon naught A by D is equal to epsilon A by D. Here, E is equal to K epsilon naught resistivity permittivity. If a resistance is placed in between the capacitor plates of T thickness and K resistivity constant, then C is equal to epsilon naught A by D minus T plus T by K. Significance of capacitor. Capacitors are used to generate strong electric fields in small areas. They are also used to store electric charges. Capacitors are used in circuits. They are used in the frequency circuits of radios and televisions. They are used to generate oscillatory electric fields and in searches. Capacitors in series. In a series circuit, capacitors are connected to each other one behind the other. The second plate of the first capacitor is connected to the first plate of the second capacitor. Similarly, the second plate of the second capacitor is connected to the first plate of the second capacitor and so on. Finally, the first plate of the first capacitor and the second plate of the last capacitor are left. These are connected to the positive and negative poles of the battery. As there is only one path for charge to flow in a series circuit, all the capacitors have an equal magnitude of charge. However, their potential differences vary. If capacitors of capacitance C1, C2, and C3 are connected to each other in a series circuit to a battery, resulting in a potential difference of V between the ends of the circuit. The potential differences that result are V1, V2, and V3. Then, V1 is equal to Q by C1, and V2 is equal to Q by C2, and V3 is equal to Q by C3. The potential differences at the ends of the series circuit, V is equal to V1 plus V2 plus V3 is equal to Q by C1 plus Q by C2 plus Q by C3 is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. The results in capacitance C and charge Q for the series circuit. Therefore, C is equal to Q by V, or V is equal to Q by C. From the above equations, Q by C is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. In the series connection, 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Capacitors in parallel. In the parallel connection of capacitors, all the first plates are connected to the one terminal, while all the second plates are connected to the other. These terminals are then connected to opposite poles of a battery. In this type of connection, the potential difference between the plates for each capacitor remains the same. This potential difference V is same as the potential difference between the opposite poles of the battery. However, the magnitude of charge is different for each capacitor. If three capacitors of capacitance C1, C2, and C3 are connected to each other in a parallel circuit to a battery, resulting in a potential difference of V between the poles of the battery, it is the potential difference between each plate of the capacitor. The charge on the first capacitor Q1 is equal to C1V. The charge on the second capacitor Q2 is equal to C2V. The charge on the third capacitor Q3 is equal to C3V. So the total charge Q is equal to Q1 plus Q2 plus Q3. Q is equal to C1V plus C2V plus C3V. If the resultant capacity is C, Q is equal to CV, hence CV is equal to C1 plus C2 plus C3 into V. Hence, in parallel connection, C is equal to C1 plus C2 plus C3.